Today we're going to be looking at predicting products of any kind of reaction, whether it be single replacement, double replacement, combustion, synthesis, or decomposition. Before we begin, I wanted to show you this concept map. It actually is a good way for us to know generally what states of matter certain substances are. Let's bring it over to this side. Substances that have intramolecular forces are oftentimes your covalent network, metallic or ionic compounds, and they are all solids, if you notice, at room temperature. Now, ionic compounds can actually dissolve or not dissolve. When they dissolve, we call it soluble, and so we designate the state of matter as aqueous. Ionic compounds that are insoluble are designated as solid. Now, moving over to the intermolecular forces, covalent compounds have intermolecular forces, and so they're divided into polar covalent and nonpolar covalent. Bringing it over to the nonpolar covalent compounds have intermolecular forces called London dispersion forces. We abbreviate it as LDF. And because those forces are very weak, these substances tend to be gases at room temperature. Polar covalent compounds will oftentimes be liquids or gases, or sometimes designated as aqueous. DDF substances are either liquids or gases. If they're liquids, they tend to be pretty volatile, which means the substance will vaporize. It has a high vapor pressure and becomes a gas very easily. If it's hydrogen bonding, you tend to be liquids or aqueous. Now, there's a category of substances that have hydrogen bonding, and that's acids. Acids are denoted by the H+ ion in that substance. Some acids are strong. The ones that are strong completely ionize, so you'll break those acids apart. Weak acids are going to ionize very partially, and so you'll see a less than 5% ionization. And in class, we talked about it as less than 10%. So it's debatable. I'd say less than 10% overall because most books will say weak acids are less than 10%. Okay? So here's the whole chart to tell you the physical states of matter generally, so that when we predict, we can figure out, we can take a good educated guess as far as what the states of matter of those substances are. So here, let's go ahead and start our practice. We're predicting the products, and we're also circling any driving force. So here I have a metal and a nonmetal. It looks like it's a synthesis reaction. So you're going to form a metal and a nonmetal will form an ionic compound, NaCl. And the state of matter of this substance, since it's ionic and it has intramolecular force, it is a solid. Okay? We won't balance any of these reactions, but we'll circle the driving force after we're done with this set of problems. Okay? So here we have a reaction where you see a compound, another compound with ions, and another ionic compound here. And so you're going to see a double replacement reaction where these two ions right here will switch places right here. Cations, or you can also switch the anions, but I like switching the cations. So sodium is now going to be with nitrate, and sodium has a +1, nitrate has a -1, so it's sodium nitrate. We're going to look up our solubility rules to see what the solubility of sodium nitrate is. So reacts, silver is with chloride. Silver has a +1, chloride has a -1, so it's silver chloride. And again, we're going to look up the solubility of silver chloride to figure out what the state of matter is. And so we're going to bring our pink sheet up. And so we're going to look to see if sodium nitrate. So I'm going to look at sodium, and I'm going to find nitrate. And I'm going to see that it's S. S means soluble, and so we designate soluble as aqueous. We're also going to look up silver chloride since we have our solubility table here already. Silver and chloride combined together is I. That means it's insoluble. So that substance is going to be a solid, silver chloride, and this is going to be aqueous. Now we look at the next substance. This has got it's aluminum chlorate. Aluminum chlorate looks like it's going to decompose because you see one complete big compound and nothing else reacting with that compound. So we know it's going to decompose. And so if you look at your reaction prediction chart, again, you're probably going to have to pull your chart back and forth here. So chlorates right here, compounds, tend to decompose into oxygen gas and the metal chloride. So oxygen gas and the metal chloride. So here's oxygen gas, and here's the metal chloride. So metal chloride is the aluminum chloride. Aluminum chloride is AlCl3. Okay. Now the state of matter of oxygen, since it's a non-polar covalent substance, is a gas at room temperature. So now predicting this product, there's no water present, so we can't really look at the pink sheet because this is for common ionic compounds in water at 25 degrees Celsius. So ionic compounds have intramolecular forces, and so that's a solid. D. In D, this is a single replacement reaction because here's our single element, and here's our compound with two or more different elements. So we're going to see that zinc is going to replace hydrogen, and we would only know if that replacement will take place using what is called our activity series. So we find zinc and we find hydrogen. Zinc and hydrogen are right here. Now when we look at them, you'll see that zinc is higher up than hydrogen, so zinc is more reactive than hydrogen, as you see the arrow showing increasing reactivity going up. So that means zinc will replace hydrogen. When zinc replaces hydrogen, hydrogen is by itself, and that's a gas. Again, non-polar covalent tends to be a gas. And then zinc is now with chloride ion. So it becomes an ionic compound. And zinc has a 2+, chloride -1, and so ZnCl2. The state of matter of this substance, since we're in solution by the denoted aqueous here in hydrochloric acid, we're going to look to see what zinc chloride is in terms of its solubilities because we're in water and it's soluble. So if it's soluble, I'm going to put AQ. Now we go to this acid, carbonic acid. We're going to decompose this carbonic acid, and we know that according to our decomposition trends, carbonates tend to break down to carbon dioxide and your metal or non-metal oxide. So here we have our carbon dioxide coming out of here. And once you pull carbon dioxide, you'll see that what's left in this substance is water, H2 and O. And that's liquid water. Okay. Now we go to the next one. The next one is sulfur. This is our non-metal oxide with water. So we're going to make an acid as a result. So the acid you're going to make is H2. So it's a synthesis reaction where you're going to combine it together. And how you know this is not a double replacement reaction is because this substance it's not made up of two ionic compounds that will then switch their ions. This is made up of the covalent and covalent. So you're going to see it synthesized together to form a bigger covalent compound. And so when you put this together, you're going to see this new acid forming. And this new acid is aqueous. Same here, I put it right next to it so you can see another acid, but this is a different acid. Instead of sulfuric acid, H2SO4, this is now sulfurous acid. We go to this next one. Looks like a double replacement. We're going to do our double replacement, NaCl plus KNO3. I forgot to leave a little room for the states of matter. And it looks like these two are aqueous, okay, according to my solubility table. I is a combustion reaction. In this combustion reaction, it is the formation of carbon dioxide, gas, and water. But water is not a liquid, it's steam, so it's a gas because this reaction is very endothermic. By the way, all these synthesis reactions often leads to the formation of heat. Okay. All right, so let's move on to the next set of problems. We've done A through I already. Now let's move over to H, J through T. Okay, I see a base, OH, and it looks like a decomp. So I see a base decomposed to metal oxide and water, liquid water. So metal oxide, barium with oxygen is your metal oxide. and it's a solid. It's an ionic compound, and water, H2O. Now, I should check to see if this metal oxide is soluble so that I know whether to designate it as aqueous. And it looks like it says it's slightly soluble, so I'm good to leave it as a solid. Okay, looking at this, it looks like a synthesis, and we're going to synthesize them together. Magnesium has a 2+ charge, fluoride ion has a -1, so it's MgF2. And again, there's no liquid water in the solution. I don't see aqueous, nor do I see water. And so I know that this is going to be a solid. And then we move over, single replacement. If you can see the single guy replacing F, but it looks like F is more reactive than Cl. So it looks like Cl can't replace F. So it's no reaction. So I'm going to lead to no reaction. I'm going to call it NR. This is combustion, CO2, gas, plus water as steam. So it's a gas, and then heat. There's light also possibly that will form out of this reaction as well. And then you go to this one. This is synthesis, forming an ionic compound, aluminum fluoride. And that's a solid. This next one, decomp. So in this decomp reaction, you're going to decompose it into its parts. So aluminum and chlorine is a diatomic molecule. So you'll notice that I have it as Cl2, and this is a gas. Here you see chlorates. Chlorates will decompose. This is decomposition. So it's going to decompose into oxygen gas and a metal chloride. So here's my metal chloride is going to be my metal right here with my chloride ion. So it's MgCl2, and that's a solid. Originally, this is a solid, so my mistake for not putting that state of matter in. Hydrogen peroxide. Hydrogen peroxide is going to yield, or you're actually going to pull out oxygen gas. So peroxides and chlorates will give off oxygen. And that will also be water. Water will be the other product. This reaction, single replacement. Notice the single one. Notice the multi-ion, the ionic compound with multiple ions. So it's going to replace, aluminum can only replace copper if it can. So let's check to see if it can. So aluminum and copper. Aluminum's right here, copper's down here. So aluminum can replace copper. It looks like aluminum is quite reactive. So aluminum is going to combine with nitrate. Aluminum has a 3+, nitrate has a -1. So this is aluminum nitrate. And then the other substance is copper. Comes out as a solid. And then aluminum nitrate, since it's an aqueous solution, let's check out the solubility table to see if aluminum nitrate is soluble or insoluble. So combining aluminum and nitrate, soluble. So it looks like I am going to designate it as aqueous. Lithium synthesis reaction, you're forming lithium nitride. Lithium has a +1. Nitride has a -3, so 3 lithiums to 1 nitride ion. So if you notice this ionic compound, you cannot look at the solubility table because you do not see water, nothing aqueous or actual water in the solution. So you can say that this is a solid that will come out of this. Carbonates. Carbonates, it looks like a decomp reaction. Carbonates yield carbon dioxide and your metal oxide. So barium oxide, BaO. And so this is a solid, this is a gas. Okay. So let's go ahead and take a quick few minutes to go back to the original, and let's circle driving forces. This is the easy part, okay? Driving forces. We see a driving force right here, solid. We see a driving force right here. Driving force for gas and solid. Gas and liquid. And heat for this one, heat for this one. This is a driving force because it's a weak acid. You won't see it ionized fully. It's kind of like treated like it's a precipitate in the sense that it doesn't fully dissolve. So it's an insoluble substance. Here you see, oh, interesting. Both are aqueous, both ionic compounds. So there's no reaction for this one. Here you see gas, gas, and heat. Moving through to the next set of problems. Here you see solid, liquid, solid, no reaction. Ooh, all three of these are driving forces. Solid, solid, gas, gas, solid, gas, liquid, solid, solid, gas, solid. Okay, so those are all your driving forces. So I hope this video helped. Let me know if you have any questions in class.